This screencast is a continuation of the previous one having to do with titrations of acids and bases. What if the acid that we are titrating is polyprotic? And the logic in this paragraph is the same if we were doing a polyprotic base. Just everything would be reversed, so to speak. So if we had a polyprotic acid, such as oxalic acid, and you can see that it is diprotic because it has its H2, and the anion is C2O4. It is diprotic. If we were to put oxalic acid into water, so in a sense here we are dissolving, and you'll notice that we go from 2 hydrogens to just 1 in front of the oxalate anion, and that 1 hydrogen ion gets connected to the water molecule, so that goes from 2 up to 3, plus the positive charge. You can see that the Ka for that is on the high side for a weak acid. 5.9 times 10 to the minus 2. Now, if this species here were to try to lose a second proton, so we're going from 1 hydrogen to 0 hydrogens, and my water molecule is going to go from 2 and pick up the hydrogen to 3 plus. In order to lose that second proton from oxalic acid, you can see the second proton, when it gets picked up by a water molecule, is 10 to the minus 5th. So that is 1,000 times less likely to happen. So when you put oxalic acid into water, you're going to get some of these, the bioxalate anion. You will have practically none or very few of these because it is much less likely. Now, having said that about a polyprotic acid, what if we are titrating? If we are titrating against a base, then this second step is going to happen after the first step is complete. In other words, once all the H2 C2O4s have lost their first proton to become H1 C2O4 minus, if we're still adding base, we can continue to drive the reaction to the right. And because we're adding hydroxides, of course, which combine with that to make water, which drives the reaction to the right. And so now all of my bioxalate ions, or hydrogen oxalate ions, will now lose their second proton and become the oxalate anions in solution. So that's what we have going on here. So let's say we're doing a titration with the weak acid, oxalic acid, and some strong base. And in a strong base or a strong acid, of course, the other, the cation or the anion is the spectator ion. The first step in the reaction is for the H2 C2O4 to become H1 C2O4 with a minus charge. But if we continue to add hydroxides, now we begin to donate the oxalate, the bioxalate begins to donate that second proton, and we're going to end up here. And once we've added enough base so that we don't have any of my original molecules or these left, and all of them are now these, then the next thing we can do is we can hydrolyze the oxalate anion. That's the only thing that's left that can happen. And so when we hydrolyze it by adding water to it, the water will donate a proton back, H1 C2O4 minus charge, and my water molecule, and I like to draw the water molecule like this, HOH, there's my hydroxide that's left behind. And now I can find my KB from that. And in a chart of Kas, they might give you the Ka, and you have to figure out the Kb by dividing it into 10 to the minus 14. So let's look at a titration of a weak base with a strong acid. Excuse me. So we'll use ammonia as the weak base, and my strong acid could be hydrochloric or sulfuric, which is diprotic, but let's just say HSO4 minus is what it turns into, or nitric acid, or iodic or hydrobromic. And you'll notice that the ammonia, NH3, is going to pick up a proton from the water molecule, which is easier to see if you write it like that, and becomes NH4 plus, and my H3O becomes H2O. So there's the hydrolysis. Now, if you had an initial molarity of 0.1 ammonia, you're not going to get a pH of 13 because this is not a strong base. You're going to get a pH that is not as basic, and we could do the math to show that it would be 11.13. That would be from chapter 17 again. That would be where if you just had the ammonia and you added it to pure water, just wanted to check up there. So if we were to take the ammonia and add it to water, we would get NHO4 plus and OH minus. And then, of course, we would say my Kb, and make sure you remember this would be a Kb, would be my products of NH4 plus times OH minus divided by NH3. And we'd plug our numbers in, and we would take the negative log of the hydroxide ion concentration, which would give me my POH. And of course, we do that because this would be point X, this would be point X, and this down here would be 0.100 minus X. So, in any case, that would be if we wanted to find the pH of my ammonia solution before adding any base at all. Now, what about later on? As the titration progresses, we're going to get more and more of these conjugates of the weak base in solution, these ammonium ions in solution. And notice we have a buffer here because we have our weak base and we have the conjugate of the weak base, the ammonium ion. So this is going to be a buffer. And that would mean that my weak base could gobble up any excess hydronium ions or H pluses, and my conjugate of the weak, NH4 plus, could gobble up any OH minuses. And in doing that, it would make NH3 plus H2O. So over here, the buffer is buffering against the addition of acid. Over here, the buffer is buffering against the addition of a base. So when you get to the equivalence point then, the only thing that's left is for your conjugate of the weak to hydrolyze. And as a result of the conjugate of the weak hydrolyzing, you produce hydronium ions. And if you're producing hydronium ions, then you can find the pH of that. And you find the pH of that in this section here, but let's quickly look at the graph. So here's my original pH of my weak base. And here's where we're trying to find the pH at the equivalence point. Weak base, strong acid, strong winds, so my pH is obviously going to be less than 7. And then here's my half titration point. Notice it's at half the volume as right here. So this is about 100, and no, this would be about whatever that number is going to be, and this would be half that number right there. in terms of the half-tite. I didn't draw the line very well. About 50. That's the half titration point. And of course, at the half titration point, that means this molarity and this molarity are the same because you have hydrolyzed, you have reacted half of it. So this cancels out, and in the end, your pH equals the pKa. And so now, at that point, you're at 9.25. So we've gone from 11.13 to 9.25 to the equivalence point 5.28. And to give you an actual example of that, we're going to titrate ammonia versus hydrochloric acid. Weak base, strong acid. If we set up our ice chart, and again, we're going to do the ice chart in terms of moles, because remember, moles is going to equal volume times molarity. Your book sometimes does volume times concentration. In any case, as we do the titration of my weak base and my strong acid, we have this at the equivalence point. We have the same volumes of each. And in other words, all the base that I started with in the bottom of my flask is now been neutralized by this much acid, this many moles of acid. Notice these moles have to equal each other because it's a 1-to-1 ratio, monoprotic. And as a result, at this point, the acid and the base have made water. And the only thing that's left are my ammonium ions, which again is in a 1-to-1 ratio, because every ammonia that splits up is going to produce a hydroxide to neutralize that and leave an ammonium behind. So it's a 1-to-1-to-1 ratio. So then when I go to find what I have at the very end, after the reaction, we can call this the E, the end in my ice chart. We take our moles and we divide it by the total volume. And the total volume would be the 100 plus the 100. And we can find the molarity. Then, of course, we can take when we find that molarity, we can find the pH from that. Now, if we have totally neutralized it, here's how we find the pH. If we have x of these and x of these, we get x squared. And here we're talking about the hydrolysis of the conjugate of the weak. And so we put my products in the numerator. They're each x. We don't know what they are yet. And we put the reactant in the denominator. Remember, all the hydroniums and all the hydroxides have canceled each other out so that all that's left is my conjugate of the weak. And now when we solve this equation for my molarity and then take the negative log of it, we get 5.28. The last thing for this screencast to talk about is a little bit about indicators. And an indicator, of course, is something that's going to indicate whether a solution is acid or basic based upon its color. And indicators are usually organic compounds, often from plants. In fact, they're often responsible for plants having the color that they have. And you can actually change the color of many flowers by making the soil acidic or basic. That's true, for example, of hydrangeas. Now, one very important point, and this is a test question. The end point is what we call the pH at which, or the point at which, an indicator will change color. That's its end point. There's a certain pH at which the indicator will go from one color to another color. That's not the same thing as the equivalence point. The equivalence point doesn't care what indicator is in the solution. The equivalence point is when you have equal moles of acid and base. So if you're going to use an indicator, you want an indicator whose endpoint, the point at which it changes color, is in the same ballpark or vicinity as the equivalence point. Otherwise, you're going to get strange results if you're relying on the indicator to tell you when you reach the equivalence point. You'll be way off. You want to choose an indicator whose endpoint is in the same region as the equivalence point. And there are many, many different indicators to choose from, based upon if you have weak acid, strong base, weak base, strong acid, or strong acid, strong base. One of the ways to talk about indicators and recognize the fact that they in and of themselves are acid and basic, we can use the letter I and D to be the indicator, and we can put H in front of it to be my proton. And when we lose the proton, IND represents the indicator without the proton, and now it's negative. It would be the conjugate, so to speak. The conjugate base of the weak acid if my indicator happens to be acidic. Now, how do we pick the correct indicator again? We want one whose color change, the endpoint, is going to be in the same ballpark as what we expect the equivalence point to be. And another way of looking at it is right here. Use an indicator whose pKa is nearly the same as the pH at the equivalence point. Sometimes you can know that from the literature, you can know that from prior experience. Sometimes you kind of have to do an experiment, or you can at least do an estimate with the math and choose an indicator whose pKa matches the pH. And that's on the test as well. Now down here, although the acidic indicator molecules also react with the base, they don't do it significantly. In other words, you might say, if I'm adding an acidic indicator to my acid, aren't I changing the pH of my solution? And the answer is not enough to make a difference, because the indicator is a very, very, very weak acid. And you're only adding a couple of drops of it as well. Another thing we should point out is that indicators are very helpful, but sometimes the indicator is not going to get you the level of precision that you might like. Here's another comment. You can buy concentrated indicator solutions, and then you can dilute them so that they go longer, because most of the time you don't need highly concentrated indicators to get the job done. Now here's an example of a bunch of indicators, and you can see that across almost the entire pH spectrum, from 0 at least up to 12, you can find an indicator that will change color for you in that particular range. Another thing we should point out is that sometimes we use indicator paper or a universal indicator solution, which will be a mixture of several of these indicators. And by having a mixture of these indicators, we can cover a partial range or the full range of the pH spectrum from 0 to 12. And again, you must choose an indicator that changes color in the range of your pH. Not any indicator is going to do. And that's it for talking about titrations and indicators.